Good morning, everyone. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn some of the definitions which are involved in the electrostatic fields. This Module 1 in electromagnetic waves and transmission lines. So, before going to discuss all the definitions involved in this electrostatic fields, so firstly, there are two major governing laws in electrostatic fields. One is Coulombs law and the other one is Gauss law. The first one, define Coulombs law means how to define this Coulombs law. Now, to define this Coulombs law, as we know that the previous classes, we'll come to know actually how the Coulombs law means in general. The force which is exerts in between two stationary charges is directly proportional to the product of those two, and it is inversely proportional to the square of the distance between the two charges is given by Coulombs law. Now, according to engineering level, we should express this Coulombs law in vector form. So that is given by the force between two very small objects, means let it be Q1 and Q2. The two charges or stationary charges are considered to be as small objects, and those two are separated in a vacuum or a free space by a distance which is large compared to their size and is proportional to the charge on each and inversely proportional to the square of the distance between those two. Right? In general, that is given by F is equal to Q1 Q2 by 4 pi epsilon naught r square into AR. Q1 Q2 are the two stationary charges, and proportionality constant is replaced by here K, that is K equal to 1 by 4 pi epsilon naught, and R be the distance between the two stationary charges, and AR be the unit vector normal to the two directions. So Coulombs law states that the force between two very small objects is directly proportional to the product of those two charges, and it is inversely proportional to the square of the distance between those two charges. Now, next one. So, the major governing law in the second law in electrostatics is Gauss law. So, state Gauss law. Definition for this Gauss law means it states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface. Means the flux is denoted with psi, and flux through any closed surface means that is given by integral S d dot ds. Flux through any closed surface is given by psi, which is integral S d dot ds through any closed surface is equal to the total charge enclosed by that surface. The total charge enclosed is given with Q enclosed. So, psi is equal to Q enclosed is given by the Gauss law, where psi be the flux through any closed surface, and it is same as that of the total charge enclosed by that surface. Means the charge enclosed is given by integral V charge enclosed. If you close that surface, then it becomes volume. Then this will gives us integral V rho V dV. So, according to the statement, the total electric flux psi which is passed through any closed surface is same as that of the or is equal to the total charge enclosed by that surface. Right? Psi is equal to Q enclosed, where psi is nothing but integral S d dot ds and Q enclosed is integral V rho V dV. Now, state applications of Gauss law in electrostatics. So, with the help of this Gauss law, we will implement some of the applications which uses internal concept as psi is equal to Q enclosed. Right? So, Gauss law is applied to find electric field intensity, and it is denoted with E bar. Means Gauss law is applied to find the electric field intensity from a closed surface. Example, electric field can be determined for a shell or for a two concentric shells or for all the cylindrical cases. Right? These are some of the applications related to this Gauss law in electrostatics. Then, next, define divergence theorem. what actually divergence theorem, why it is, how it is applicable to the electrostatics. So define divergence theorem means the integral of the normal component of any vector field, integral of the normal component of any vector field over a closed surface integral means integral is a dot ds, where vector A is the A be the vector and the differential surface area is represented with ds. The integral of the normal component of any vector field over a closed surface is equal to the integral of the divergence of this vector field throughout the volume enclosed by that closed surface. So divergence theorem gives us the relationship between surface to volume integrals. That is closed surface integral S A dot ds is equal to integral V del dot A dv. See here, this gives us the divergence theorem gives the relationship between surface integrals to the volume integrals, and it is given by closed surface integral S A dot ds is equal to integral V del dot A dv, where del dot A resembles divergence of any vector field. So integral of the normal component of any vector field over a closed surface integral is equal to the integral of the divergence of this vector field throughout the volume enclosed by that closed surface. So if you evaluate this closed surface integral, then it becomes volume. Right? So based upon this divergence theorem, we can prove means if we close that line, then it becomes volume, and it gives the relationship between surface to volume integrals. Then, what are the significant physical differences between Poisson's and Laplace's equations? Right? So, there is a difference between this Poisson's and Laplace's equation. Whereas Poisson's law is given by del square V equal to 0, whereas this Laplace's equation is given by del square V equal to 0, and this Poisson's law is given by del square V equal to minus rho V by epsilon. For a charge-free region's case, if rho V equal to 0, where rho V be the volume charge density, if rho V equal to 0, then Laplace's Poisson's equation becomes Laplace's equation. See, when the region of the interest contains charges, Poisson's equation can be used to find the potential. And when the region is free from the charge, Laplace's equation is used to find the potential. In order to find the general case, both the Poisson's and Laplace's equations are need to be used in order to calculate electric potential. That is the term which we have considered as a notation as V. So when the region of interest contains charges, then Poisson's law is to be applicable to measure electric potential. Similarly, when the region is free from charge, there is no charge inside that. Hence, if rho V equal to 0, then del square V equal to 0, then that is the equation called Laplace's equation. This is the a significant difference between the Poisson's and Laplace's equation. Right? If the region consisting of some charges, then Poisson's law is to be used to measure electric potential. When the region is free from the charge, means there is no charge inside that. That is the case. Laplace's equation is used to measure the electric potential. Then define current density. So in general, we know that current is nothing but it is a flow of charge. A flow of electrons is nothing but charge, and current is generally measured in amperes. 1 ampere is equal to 1 coulomb per second. Right? So in general, 1 ampere is equal to Q by T. This can be defined as charge per unit time, and here current density means the current density at a given point is the current through a normal area at that particular point. So current per unit density. Current density can be given by here current per unit normal area, means generally it is denoted with J, and it is given by J is equal to integral I current in terms of current densities is given by I is equal to integral S J dot ds, where J be the current density. So depending upon this current density, we'll have three different current densities: displacement current density, conduction current density, and convection current density. Whereas if you compare conduction and convection, conduction current density require conducting medium to conduct, then your current density means the current per unit normal area at that particular point is given by current density. So that is given by current in terms of current densities, means we can express that as I equal to integral S J dot ds. Right? So here the divergence theorem gives us the relationship between surface to volume integrals, and the physical difference between the Poissons and Laplaces means if the the region of interest contains some charges, then the Poisson's law can be used to calculate electric potential, whereas when the region is free from the charge, means there is no charge inside that, then Laplace's equation is used to find electric potentials, where that equation is given by del square V equal to 0 and del square V equal to minus rho V by epsilon. If del square V equal to 0 is said to be Laplace's equation, and Poisson's equation means del square V equal to minus rho V by epsilon. Similarly, now to define this current density, we used to consider here first current, that is 1 ampere is equal to 1 charge per 1 coulomb per 1 second, and from this current density can be defined as current per unit normal area at that particular point, and it is given by I is equal to integral S J dot ds. Yes. Generally this J is measured in current density, current per unit area. Generally current is measured in amperes, and per unit area means that current density measured in ampere per meter square. Next, define linear, isotropic and homogeneous dielectrics materials. Okay, so to define or to differentiate isotropic, linear and homogeneous dielectric materials, see, these are the depends upon the characteristic parameters, which are epsilon, permittivity, and mu as the permeability. So depending upon that, here a material is said to be linear. Then electric flux density varies linearly with electric field strength, where electric field strength is denoted with E and flux density is denoted with T. Then these two, the relation between two is given by T equal to epsilon into E. So material is said to be linear case, electric flux densities varies linearly with electric flux field strength or electric field intensity. See, if you increase the value of D, E is also increases. This is the case, the material is said to be linear dielectric material. Then, a materials for which permittivity does not vary. Permittivity means we are representing it with epsilon, and the material for which epsilon does not vary in the region being considered and is therefore same as all the points are said to be in homogeneous. It will distribute in the equal distances of all directions, then it is said to be homogeneous dielectric material. Means the permittivity is fixed for that. See, materials for which permittivity does not vary in the region being considered and is therefore that is the same at all points are said to be homogeneous dielectric material. And the other case is the isotropic type. So isotropic type materials for which electric flux density and electric field strength are in the same direction are said to be isotropic. So this is the difference between, depending upon the flux density and the field intensity variations, we will identify different types of dielectric materials as under linear and isotropic and homogeneous type dielectric materials. Right? If D and E are linearly increases, then the materials are said to be linear dielectric materials. And if epsilon, that is permittivity, is won't vary for that, and that is same for all the points, all the directions, then the type of materials are said to be homogeneous dielectric materials. And if the materials for which electric flux density and electric field strength are in the same direction, then those are said to be isotropic type materials. Okay, so this is a fundamental difference between linear, isotropic and homogeneous dielectric materials. Next, define Stokes theorem. So similar to that of divergence theorem in electrostatic fields, this also exists. This Stokes theorem gives us the relationship between line to surface integrals. Okay, so it states that circulation of a vector field A around a closed path. Closed path resembles we are considering here with respect to the line. So closed line integral L A dot dl. So length L stands for line here. Length we are considering, hence this differential component is given by dl. Right? It states that circulation of a vector field around a closed path is equal to the surface integral of the curl of a vector over the open surface. So, which is equal to integral is curl of a vector. We are representing it with del cross A dot ds. Okay. See, define Stokes theorem means the Stokes theorem gives us the relationship between line to surface integrals, and it is given by states that circulation of a vector field around a closed path, that is integral L A dot dl, closed line integral L A dot dl is equal to the surface integral of the integral S curl of a vector del cross A over dot open surface, that is given by integral S del cross A dot ds. Okay, so define Stokes theorem means according to the definition of a Stokes theorem, it gives us relationship between line to surface integrals, and the mathematical statement for that is given by closed line integral L A dot dl is equal to integral S del cross A dot ds. So circulation of vector field around a closed path is equal to the surface of the integral of the curl of a vector over the open surface. Hence, from this equation, we can say that which gives us the line to surface integral in the theorem which belongs to this electrostatics are said to be Stokes theorem. Suppose if we consider it for divergence theorem, it gives us surface to volume integral relationship. Then what is relaxation time? Next one is what is relaxation time? So it is the time. It takes the charge placed in the interior of a material to drop to 36.8% of its initial value. So, and mathematically we can write it as tau is equal to epsilon by sigma. Then relaxation time. The time it takes to charge charge placed in an interior of a material to drop to 36.8% of its initial value. 36.8% means nearly it is reduces 37% of its original value. Okay, so this gives us relaxation time, and it is mathematically we can express this in terms of equation as tau equal to epsilon by sigma. See, define linear. So from this uh, one, linear, isotropic, and homogeneous dielectric materials differences we have learned. The fundamental one is when the material is said to be linear dielectric material means the relation between flux density and field intensity are same, means if both are linearly increases, then those materials are said to be linear dielectric materials. And the materials for which permittivity does not vary in the region being considered and is therefore and it is small at all points is said to be homogeneous dielectric materials. Next is the isotropic one. To define this, materials for which electric flux density and electric field intensity both are in the same direction or in the same direction, then those materials are said to be isotropic dielectric materials. Generally, the dielectric materials are nothing but insulating materials. Okay, then Stokes theorem. To define the Stokes theorem, we must know the how it gives the relation between any two. Means if it is gives the relation between line to surface or surface to volume, like that. So here, depending upon the Stokes theorem, we will derive the relation between line to surface integrals. So it states that circulation of vector field around a closed path, and it is equal to the surface integral of the curl of the vector field over a open surface. Then it is said to be Stokes theorem. Right? So closed line integral L A dot dl is equal to integral S del cross A dot ds. Right? And the relaxation time, it gives us the relationship between tau equal to, mathematically we can write the equation as tau equal to epsilon by sigma, and it is measured in seconds. Relaxation time, and it is derived from the one of the Maxwell's equation called Gauss law for electrostatic fields. Next, then define capacitance. What do you mean by capacitance? The capacitance of this two conductor system as the ratio of the magnitude of the total charge on either conductor to the magnitude of the potential difference between two conductors. So generally it is given by C is equal to Q by V. The notation for this capacitance is given by C, and it is gives the relationship between, means suppose if we have two parallel plates with which carries, one is positive charge and another one is filled with negative charge, and the potential difference between two is given by this V, and charges are plus Q here minus Q, then this is the case. The capacitance is defined as a capacitance of this two conductor system. Generally it is a capacitance also a conductor, then conductor system as the ratio of the magnitude of the total charge on either of the conductors, means either if you consider positive charge or else negative charge, then that is given by C equal to Q by V. Then the Q is given as one of the charge on parallel plate capacitors, and can be in the numerator, that charge Q can be considered either of the charges of the parallel plate capacitors, and V be the potential difference between two, and it is very small when compared to the other things. So C equal to Q by V. So capacitance means the capacitance of this two conductor system as the ratio of the magnitude of the total charge on either of the conductors to the magnitude of the potential difference between the two conductors. So mathematically we can write that equation as C equal to Q by V, and capacitance C is measured in general farads. Okay. Then define electric field intensity. So the force per unit charge when placed in the electric field is called as electric field intensity. Then it is also said to be electric field strength. Electric field strength. Right? So force per unit charge. Generally the electric field intensity is denoted with E, and it is also a vector. We are representing it with E bar. Right? So electric field intensity E bar is given by force per unit charge when it is placed in the electric field. Force per unit charge. Hence the unit are given by Newton per Coulomb or sometimes volts per meter. Okay. So define electric field intensity means this electric field intensity is also called as electric field strength, and it is defined as is the ratio of the force per unit charge when it is placed in a field called electrostatic field. Right? So in general it is given by E equal to F by Q, and from the force, the Newton equation, force can be measured in newtons and the electric charge can be measured in coulombs. Now from that, electric field intensity is in general measured in volts per meter. Now according to the definition, it is to be measured with respect to newtons per coulomb. Next, define electric potential. Where to define this electric potential, first, it is the amount of work needed to move a unit charge from a reference point to a specific point against an electric field. Right? So electric potential in general, we just consider the notation for that is V, work done per unit charge is said to be the electric potential. See, the amount of work needed to move a point charge or a unit charge from a reference point to a specific point against in an electric field. Right? So V equal to W by Q. Work done per unit charge when it is considered to be between two reference points. and it is particularly related to electric fields. Okay, so in general, in short, how we'll define in short, the easy way how we'll define this electric potential means it is the potential difference between the two reference nodes, and sometimes it may also defined as work done per work done means in order to move the charges from one place to the another place we need to apply some energy. So that is given by here work done. The work done per unit charge when it is placed in electrostatic fields, then it is said to be electric potential, and mathematically we can write the equation for that as V equal to W by Q. Right? So work done is generally measured in joules and per charge can be measured in coulombs. So generally this electric potential is nothing but electric voltage, and it is measured in voltages. Okay? Then define conservative electric field. Right? So any electric field that satisfies the closed line integral of the field is zero. Electric field that satisfies the closed line integral, closed L line integral of the field, that is V E dot dl is 0. See, field component means related to the electrostatic fields, we are representing it with E. So an electric field that satisfies closed line integral of the field. So closed line integral means closed circle integral L E dot field is considered to be as the electric field intensity E bar equal to E bar dot dl bar equal to 0 is said to be a conservative electric field. Right? So in this is the integral form. If you consider the point form, then if you on based upon the by application proper application of Stokes theorem, then it gives us the point form or differential form of the Maxwell's equation for the electrostatic fields related to this conservative electric fields. Then it is given by del cross E bar equal to 0. Okay. So define a conservative nature of the electrostatic fields. So that is an electric field that satisfies the closed line integral of the field is 0 is said to be a conservative electric field. Right? So in this what we have learned is define, first of all we have learned how to define the capacitance, then from that electric field intensity, then from that electric potential and conservative electric field, how to define all such parameters we have learned this particular bit. See, define capacitance means that generally we are representing it with the capacitance means the notation is C, and it is the two conductor system. Basically it consisting of two conductors, and it is the ratio of the magnitude of the total charge on one of the plates of the parallel plates and to the magnitude of the potential difference between the two conductors is given by and defined by the capacitance, that is C equal to Q by V. Then define electric field intensity. So to define this electric field intensity, we must know how do we cover this electric field intensity in the other way. So this electric field intensity is also called as electric field strength, and it is given by, it is the generally it is defined as force per unit charge when it is placed in electrostatic fields. Then mathematically we can write the equation for that as E bar equal to F by Q, where F be the electric force and Q be the electric charge, and those two can be measured as Newton per coulomb or sometimes volts per meter. And after that, electric potential. So electric potential is nothing but electric voltage or potential difference between the two reference nodes. Or sometimes it may also defined as the amount of work needed to move a unit charge from a reference point to the and the specific point and against in the electrostatic fields. And it is given by V equal to W by Q. W is the notation for work done and Q be the charge, that is electric charge. So V equal to W by Q, and in general we use the notation for electric potential or electric voltage is as V, and it is measured in volts. Next is define conservative electric fields. So any electric field that satisfies the closed line integral of the field is zero. Closed line integral means integral line means we are representing it with integral L, and where closed means we are talking about closed, hence we are supposed to consider an electric field that satisfies the line integral, closed line integral, hence closed line integral L. The field component is here E, that is represented with electric field intensity as E bar into dl, differential length, that is given by closed line integral L E dot dl is equal to 0, then is said to be a conservative electric field. Right? So if you apply, this is the integral form. So if you want to, sometimes we used to consider conservative electric field mathematical equation means in the differential form or the point form, we will write it as del cross E bar equal to 0. So by proper application of Stokes theorem to this closed line integral of the field is 0, then it becomes del cross E bar equal to 0. Okay. So this is the definition related to conservative electrostatic field. So this is the electric field that satisfies the closed line integral of the electric field intensity is 0 case, and it is said to be conservative electrostatic field. That is closed line integral L E dot dl is equal to 0 and del cross E bar equal to 0. Next, define electric flux density. Then what is an electric dipole? And after that, point form of Coulombs law. First, we are going to learn what is electric flux density. So, electric flux density can be measured. Generally, that electric flux means flux. How can you define this? Flux means number of lines of force is said to be flux, and number of lines of electric lines of force is said to be electric flux, and passing through a given area is said to be electric flux density. So that can be given by here. One line of electric flux emanates from plus 1 coulomb plus q and terminates on minus 1 coulomb, that is minus q. Therefore, the electric flux is measured in coulombs. Generally, the flux can be electric flux is nothing but electric charge, and it is measured in coulombs. Hence, the vector field D means now to represent this electric flux density, we use the notation as D, where D is also a vector. So, hence the vector field D bar is called the electric flux density and is measured in coulomb per square meters. Means D is equal to epsilon into E. So, here epsilon is measured in farad per meter, and where this E is measured in volts per meter, right? So D is generally measured in here, D coulomb per meter square. Electric flux passing through a given area. The total number of lines of force which is passing through a given area is said to be electric flux density, and the relation between flux density and field intensity is given by this D equal to epsilon into E, right? So T be the electric flux density and is measured in coulomb per meter square, where E be the electric field intensity. It is also called as electric field strength, and it is measured in volts per meter. Where flux density, this electric flux density is also called as electric displacement, right? So total number of lines of force which is passing through a given area is said to be electric flux density, and it is measured in coulomb per meter square. Next is, what is electric dipole? So an electric dipole is formed when two point charges of equal magnitude. Suppose if I have a point charge Q is here plus Q, and another point charge is located at a particular point and it is represented with minus Q, and these two are separated by a small distance D, then the concept is said to be, or the term is said to be, electric dipole. Dipole means which exist two polarities, two charges, carries two charges. Means an electric dipole is formed when two point charges of equal magnitude but the opposite sign are separated by a small distance. But two are having two charges means Q and Q only, but the directions in which they are moving are different. Right? And the distance which are separated by these two are very small in distance. Right? So electric dipole means electric dipole is formed when two point charges of equal magnitude but opposites are in sign and those two are separated by a small distance is called electric dipole. Next, P is given by here small p electric dipole and moment is given by P equal to Q into D is given by electric dipole moment. Then state point form of Ohm's law. Point form of Ohm's law. So Ohm's law is given by here V equal to IR in general in the circuit theory. The Ohm's law is given by the potential difference between two nodes is directly proportional to the current which is flowing through that wire. Then where R is said to be proportionality constant, then in general Ohm's law means we'll define it as V equal to IR. Point form of Ohm's law states that the field strength within a conductor is proportional to the current density. So that is given by here J is equal to sigma into E bar. The field strength within a conductor is directly proportional to the current density. So E is directly proportional to the current density as J. So E is analogous to V in the circuit theory, where I is analogous to J in the field theory. Right? So where the point form of Ohm's law states that a field strength within a conductor is proportional to the current density, and it is where proportionality constant is replaced by sigma, which is equal to J. Right? So J equal to sigma into E is said to be conduction current density, and it is also said to be point form of Ohm's law, which is to be derived in the case of one of the Maxwell's equation in electrostatic fields. Okay, point form of Ohm's law means how it is analogous to normal Ohm's law means a point form of Ohm's law states that the electric field within a conductor is directly proportional to the current density. Right? Where that proportionality constant, if you replace it with conductivity, that is sigma, then that is analogous to how it is analogous to means E is analogous to V and J is analogous to I and sigma is nothing but or analogous to R in normal Ohm's law. So in this PPT, that electric flux density we have learned. Electric flux density means electric lines of force which is passing through given area is said to be electric flux density, and gives the relation between electric flux density and field intensity as D equal to epsilon into E. Then it is measured in Coulomb per meter square. Next is what is electric dipole? So electric dipole is formed when two point charges of equal magnitudes and these two are differed by a small distance, but the direction in which they are moving are in opposite. In general, that electric dipole moment is called as or gives us the mathematical expression as P equal to Q into D. And state point form of Ohm's law means the point form of Ohm's law states that the field strength within a conductor is directly proportional to the current density, and it is given by E is directly proportional to J, where that proportionality constant is replaced by sigma. Sigma is said to be conductivity of the material. Okay, so what we have learned is some of the definitions related to the electrostatic fields we have learned. That is two major governing laws in electrostatic fields are Coulombs law and Gauss law, where drawback which is exist in the Coulombs law is nothing but it is not applicable for the symmetrical charge distributions. For the symmetrical charge distributions case, Gauss law is applicable. According to the Gauss law, that is the flux which is passing through any closed surface is same as that of the net charge enclosed by that surface. Mathematically, we can write the equation as psi is equal to Q enclosed. Then after that, we have discussed some of the applications related to that Gauss law. Then after that, we have learned how to define electric field intensity, that is electric force per unit charge when it is placed in electrostatic fields, that is mathematically we can write E equal to F by Q. And electric flux density definition also we have learned, that is electric lines of force which is passing through a given area, and generally it is measured in coulomb per meter square. And after that, point form of Ohm's law, then current densities already we have learned. The current density means current per unit area, and it is generally measured in ampere per meter square. Different types of current densities already we have learned. It is convection current density, then conduction current density, and displacement current densities. Right? So, point form of Ohm's law gives us the analogy between normal Ohm's law and the point form of Ohm's law. Is the difference is it is exists in Maxwell's equations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.